Okay, so yesterday we ended our class with the definition of coordinates of a vector. So if you recall, the coordinates, we represent a vector in Cartesian, uh, in a coordinate system, and the usual coordinate system is the Cartesian coordinate system. But it's not necessary that we always have to represent a vector in terms of that kind of coordinate system. So what I mean that, so let's say there is a same vector, and you have these grids, and let's say this is your 0 comma 0 is origin, and this is the Cartesian coordinate system, and you take the unit vector along this direction e1 and the y-axis e2, and any vector can be represented by uh, the coordinates. For example, if I say this is 1 comma 1, okay, so you know that this is e1 plus e2. And let's say that you have a friend, and the friend looks the space in uh, the friend has a problem to look into this space. I mean, so for him, the space is looks little different. Hmm. And let's say for him, uh, he, here in this grid, every lines are parallel and perpendicular to each other. But what he says, let's say that lines are also parallel, but let's say that it is something like this. So this may not be the perpendicular, but what we can see, let's say this is the x-axis for your friend, and this is the y-axis for your friend. So along this, if you take the unit vector, let's say I say this is b1, and along this y-axis, the unit vector is, let's say, b2. Then you have to represent this point, the same point, in his coordinate system. So then the coordinate definitely may not be 1 comma 1, which is in your coordinate system. So that's why we always represent a vector. When we say that in terms of coordinate, we have to say that how the axis, I mean the bases look like. So that's why the definition of the coordinates will be always with respect to a set of ordered bases, because of this ordered, it's not unordered basis. Because of this ordered, the coordinates will be dependent. So if you have the basis b1 to bn, and if you can represent a vector v in terms of the linear combination like this, then the coordinate of this vector v will be represented by this n tuple c1 to cn with respect to the basis b, and we sometimes denote it by like this. Okay, we just take an example and proceed further. Let's say we have a vector v in the usual coordinate system, or the standard, with respect to the standard basis. the coordinates are this. And let's say we have given a ordered basis, say B, here the basis order is 1 comma 1 comma 1, 1 comma 1 comma, let's say 0. Another is, let's say, 1 comma 0 comma 0. And we have to find the coordinates of D with respect to this basis capital B. How will we do that? So we have to represent these vectors as a linear combination of this basis. Let's say this is C1. So let's write down, let's take another constant C2, 1, and C3, 1 comma 0 comma 0. And if you solve this equation, I'm not going to solve it. So if you solve this equation, you will get that C1 equals to 1, C2 equals to 2, and C3 equals to minus 2. So this implies that the given vector V with respect to the coordinate system formed by the basis B will be, or can be, will be represented by 1 comma 2 comma minus 2. Okay, is it clear? So this is the same vector, but we are representing with a different coordinate system. The coordinate system is based on this set of bases. Okay. If it's clear for you, then you try to figure it out at home. This just the opposite. Let's say find the vector V in R3 whose coordinates vector relative to the ordered basis B, or B is given like 1 comma 1 comma 1, or let's say 1 comma 1 comma 0, or let's say 1 comma 0 comma 0. And the coordinate with respect to this basis is 3 comma 2 comma 1. Now what will be the coordinate in the usual and standard system? That means where the basis will be the standard basis E1, E2, E3 that you have to figure it out. I hope you can do that. So just try at home. Okay. Any question, doubts about this representing a vector in terms of coordinates? Okay. If not, then we proceed further. Now we discuss about the linear transformation. Okay. So linear transformation, first I write down what is linear transformation. A linear transformation, or sometimes it's called also mapping, transformation, or sometimes called the linear map, and so we denote by T, from a space V to another space W is a map is a map which satisfies the following equation or following property. What is that property? That if you take the linear combinations of any two vectors from V, let's say I take linear combination alpha V1 plus beta V2, then we'll have alpha T of V1 plus beta T of V2. This will be for, this is true for all alpha, sorry, all vectors, a pair of vectors V1, V2 belongs to V, and alpha, beta are real numbers. Okay, and of course, what I said that this linear map is from V to W. So here V can be R, in our case V can be R square, or V can be R cube. Also W, it can be R or R square or R2 or R3. Okay, now we have a note. The important stuff is that if you have a linear transformation T, and if you give the input the null vector in V, because these two spaces could be different. Let's say V is R2 and W is R3. So null vector will be also different. In R2 it is 0, 0, and R3 it's 0, 0, 0, right? So the space could be different. That's why null vectors could be different. But if you take the null vector as the input in this linear transformation or linear map, it will give you the null vector in the other space. Okay, it will always be there. This is very important for the linear transformation. And of course, if we take, I mean, we can see that if you take alpha and beta equals to 0, you get that. Okay, if this is the case, then another important step, that if you take any vector, let's say you have a transformation T prime, and T prime, if we take any vector V, and it gives V plus some constant vector V naught, if this is the case, then it will not be linear. Then this T prime is not linear transformation of course, where V naught is not the null vector, it is a constant vector. Why will it not be linear transformation in this case? Anyone?
Sir,
If we
it
have a
will not satisfy that above equation.
right, right. In that case, if you just put V equals to the null vector, then it will not transform into the null vector in the other space. That's why it will not satisfy that property. And this kind of transformation is something like shifting. you're just shifting. If you take any coordinates, you're just shifting. So that's why the shifting transformation, we have different transformation like rotation, reflection, shear. We'll discuss that little later. But shifting, this transformation is not linear transformation. That you have to keep in mind. Now let's say a simple case when V equals to W, that means they are the same space. The important is that any two parallel straight lines becomes two parallel straight line after the linear transformation. Become two parallel straight line. Okay. So sometimes people say that these two are also very important to judge visually that some transformation is linear or not. Is 1 and 3, you can decide that some transformation is linear. Okay. Now let's have
So,
some mathematical example. Yes, Gaurav?
so this third point, uh, can you please explain that when any two parallel straight lines you are talking about, aren't they becoming the same lines? Because both
No,
of
no.
them must pass through null vector.
Uh, what I mean that geometrically, let's say that if you have, let's say you take the usual coordinate standard with respect to the standard basis and you have these two lines. Okay. So after the linear transformation, maybe these two lines becomes like this. Okay. So they will
Sir,
become the,
yes, sir, but these two lines are not subspaces. These two lines in the first diagram that you draw.
oh, no, 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 no. What I mean that these two straight lines from V is a space, means subspace or vector space, whatever you say. These two lines in V will become a two straight lines, parallel straight lines in W.
Oh, okay, sir. Okay.
In V becomes two parallel straight lines in
Okay,
W.
sir.
That's what I mean. Okay.
But we assumed V is equal to W, right?
In this case, we assume that V is equal to W. Yes.
Yeah.
Okay. Now take an example. Let's say that we have a linear transformation, or we have a transformation. We have to figure out that is linear or not. Or it maps from R2 to R3, and the map is defined by. So if you take a vector with the coordinate x comma y, then it will give you. Of course, you have to give it needs to produce a vector in R3, and then the coordinates will be x comma x plus y comma y. Okay, and we have to figure it out that this is linear transformation or not. So let's take two vector from R2. Let's take two vector. Uh, the coordinates are x1 comma y1, and v2 the coordinates are x2 comma y2. And then one hand we'll just see that this holds or not. So then we calculate the left hand side of the equation and also separately calculate the right hand side of the equation and see that they will be equal or not. So this case, then take two some arbitrary two real numbers alpha beta, then alpha v1 plus beta v2. So this means t of alpha x1 plus beta x2 comma alpha y1 plus beta y2, right? And now we apply the definition of this transformation. We'll get alpha x1 plus beta x2 and alpha into x1 plus y1 plus beta into x2 plus y2, and the third coordinate will be alpha y1 plus beta y2, right? So this is the left hand side of the equation. We also separately calculate the right hand side of the equation. So t alpha into t v1 plus beta into t v2. So this is alpha into, if we apply the definition of the transformation, then it is x1 comma x1 plus y1 comma y1 plus beta into x2 comma x2 plus y2 comma y2. And with this, what you can see that alpha x1 plus beta x2 comma alpha x1 plus y1 plus beta x1 x2 plus y2 x2 plus y2 comma the third coordinate will be alpha y1 plus beta y2. Okay, let's say this is 1 and this is 2. So from 1 and 2, it implies that we have alpha v1 plus beta. Transformation of this is alpha t of v1 plus beta t of v2. So that's why t is a linear transformation. T is a linear transformation. Okay, is it clear? I take another example. Okay, it's again map from R2 to R3, and let's say that map is defined by tx comma y equals to x, y, and x into y. And we have to verify that t is a linear transformation or not. We can take v1 equals to x1, y1, v2 equals to x2, y2, and then just verify. We have to proceed in the same way. And sorry, alpha x1 plus beta x2 comma alpha y1 plus beta y2. Okay. Now, I'm not going to write the first coordinate and second coordinate. I'm going to write down the third coordinate because they'll there a problem might occur because we have this kind of term x into y. So the third coordinate in this case, I mean, for working on, I mean, you is complete at home, but when we find the third coordinate, this is alpha square x1 into y1 plus alpha beta x1 y2 plus x2 y1 plus beta square x2 y2. So this is the third coordinate. And on the other hand, if you compute t alpha into t v1 plus beta into t v2, just try to figure out the third coordinate. Okay, first of all, it will be x1 y1 x1 y1 plus beta x2 y2 x2 into y2, right? Then let's see the third coordinate. Third coordinate, what we will figure it out, it will be alpha x1 y1 plus beta x2 y2. And what you can see that here the third coordinate was this quantity, but here the third coordinate was this quantity. So that's why definitely this will be not equals to t of alpha v1 plus beta v2. And that's why in this case, this transformation t is not linear. This implies t is not linear. Okay, up until now, any doubt, question? Please let me know, because we'll proceed further. So you should clarify your doubt if you have. I just gave you 2 examples.
Sir,
Yes.
sir, in the when you are doing the transformation from V to W, uh,
Hmm.
he he is having some dimension. So will the dimension of that vector space change on transformation? Because it is not changing in the examples that you saw.
It's changing. So, for example, you take any example, let's say 1. So it's from the 2D space to 3D space, right?
No, sir, the dimension of that dimension of the vector space we are generating in that 3D. For example, here from t x comma y to x comma x plus y comma y.
Right.
Here
So
also,
dimension changed. So it's a linear transformation from R2, a plane, to a 3D space, right? So a point, I mean, usually we represent in terms of coordinate system, a vector is represented. So that means a point in R2 in a plane will be transformed to a point in a 3D space. So that's why these two are different space, right? One is R2, some plane, another is R3 in a 3D space. So that's why one point will be represented by 2 coordinates in a plane, that is x comma y, and then when it transforms, the point will be represented by 3 coordinates in R3, and here it was given x, I mean the formula is given x comma
yes,
x
sir,
plus
but
y comma y.
ultimately in the 3D space, suppose if you are transforming a plane by some linear transformation, here the suppose the xy plane.
Hmm.
So in that R3, will it
Hmm.
give a it will give a plane?
The whole space or not?
Yes, sir. Means it will not give a
Oh,
three. Yes.
okay, whole space or not? Okay, okay, that is your question. Okay, we'll see with different examples, and you have to. So please keep this question in mind. Your question is that if you have a linear transformation that is a plane, and is it possible to have a linear transformation that the plane will be transformed into the whole
Yes,
space?
yes,
So, so whatever we get, the the uh, codomain of this transformation, will it be still a plane, or can it be the whole R3? Right, that
yes,
is your
sir.
question. So please keep this question in mind, and we explore more, and the examples it might be clear.
So one point
That
I
is a
had,
very good observation.
yes, sir.
Yes.
Actually, one point I had that when you are transforming R squared to this R3, you are actually
Hmm.
giving a constant on one of the three coordinates. Means when you are suppose
Right.
in the, if you fix one and third coordinate x and z coordinate in R3,
Hmm.
you cannot
Hmm.
arbitrarily choose the second coordinate. Suppose,
Right. Right. Right.
yes,
That I can get your point, because on the other hand we have two variables for two coordinates x and y, and if we have to
yes,
create the
sir,
three variables, so then one variable must be dependent on the other two.
yes, sir,
Then the linear dependence will come.
yes, sir. So I was thinking that how
Right.
is the
Right.
dimension?
Right. 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 You're thinking in very right direction. So until the examples we have, we are thinking the right direction. Okay. But remember that we are bounded with the R2 and R3, these examples. Okay. So now we proceed further with we discuss, we have, let's say we have a discussion on a simple case that is map from R square to R square. We're discussing a simple case, then we will extend uh, that the different space. So what is happening? Let's okay. Let's say this is origin. And we have a vector, let's say v equals to -1 and 2. So -1 comma 2. So in this case, of course, this is our E1 and this is our E2. And -1 comma 2, that means 1 comma 2 this point. So this is our -1 comma 2. Fine. Now let's say that we have a linear transformation. And after the transformation, the space, I'm just drawing on the same grid. Okay. But you can imagine this, the first R2 and the second R2 are different. So I'm using the different colors, but I'm drawing on the same, uh, the overlapping one picture with the another one. So let's say that after that, the grids becomes like this. Okay. So, and let's say that now, so this was the vector v. Now the vector v transformed and becomes somewhere. But what does it go? We have to figure it out. So before figuring out that what does it go after this transformation, we just figured out what does this E1 and E2, the standard basis, those two vectors go after the transformation. And let's say, for this example, let's say the E1 in the new space sorry, my picture, I'm drawing very bad picture. Let's say this becomes, so this is T of E1. Okay. And let's say this becomes T of E2. So can you imagine that what's happened? It was some sort of rotation had happened. Not only the rotation, now here, I mean, the perpendicular uh, vectors are not perpendicular anymore after the transformation. For example, E1, E2 was perpendicular. Now, after the transformation, whatever we have the T1 and E2, they are not perpendicular anymore. Okay. And let's say that your have to extend the grid. Let's say this is my new V. So this is, let's say, TV in the new space. So it was V before, and now this is the TV. So we have to then, what I said that we have to figure it out, what does this V goes? And what I said that, what at the V goes, to know that what does the V goes, we just need to know that where does this E1 and E2 goes. Now, as you know that in the previous space, the V was, the coordinates was -1 and 2. What does it mean? That means a -1, this constant, into E1 plus 2 into E2, right? And let's say that just for this, and just I give you an example. Let's say your E1 now becomes 1 comma minus 2, and after the transformation E2 becomes 3 comma 0. So that means mathematically, if we apply this linear transformation T on V, so that means we are applying on this, right? And since T is linear, we can write in this way. So that means now we apply the coordinates of these vectors. So this means we can write down -1 into, let's say, 1 plus 2 into 3, and -1 into -2 plus 2 into 0. And this can be written as 1 minus 2, 3, 0, this matrix, and -1 to 2, a vector. And what you can see that this is actually vector V. If you remember, V is -1 comma 2. And here, this portion actually nothing but T of E1, and this portion is nothing but T of E2, right? And what we get, that is TV, right? So TV now represented by a matrix where the first column is the coordinates of TE1, the second column is the coordinate of TE2, and then we multiply V with this matrix and we get we'll get the new coordinates of TV. Where does it go? Actually, we will get it 5, 2. So these are the new coordinates. So that means uh, if you take any arbitrary V and that multiply the coordinates of V with this matrix, you will get the new coordinates of V after the linear transformation. Okay, I just write down. So that's why so that means if we know where does E1 go after the linear transformation, and where does E2 go after the linear transformation, that is the new coordinates of T, I mean that is TE1 and TE2, then we can find where does a vector V goes after the linear transformation. This is for all V belongs to R square, right? So just give you an example. For example, let's say we represent a internal X and Y, and we want to figure it out the TV. So what do we have to do? That we have to then take the uh, matrix where the first column will be TE1, the second column will be TE2, and then we have to multiply with X and Y. So this is nothing but the matrix is what we know that here, that 1 comma minus 2 and 3 comma 0. So 1 comma minus 2, 3 comma 0, multiply with X and Y, it gives us X plus 3Y and minus 2X, right? So that means this linear transformation T is actually, we are describing this linear transformation. So we don't know the formula of this mapping T. But what we know that instead of knowing the formula of this mapping, we know that what does that E1 goes and what does that E2 go. So if we know this information, we can construct a matrix which describe this linear transformation T. So that means T can be described by the matrix. In this case, the specific matrix is 1 minus 2 and 3 and 0. Is it clear? Any doubt, question until now?
So
Yes,
can you go to the
Pritesh?
previous picture?
I have
Yes, yes,
already
yes.
gone, but there is a
So why
lag.
you draw these diagonal lines, dotted diagonal lines?
Oh, I said that. I mean, what happens? Of course, I mean, for any linear transformation, uh, if it is in the same space, then parallel lines will become the parallel lines. So I just to show that the grids changed, but it will be parallel actually.
Sir, actually, you should have shown TE1 along that dotted line. Means
Right, right, right,
Yes.
right. So my
since your
picture is
TE,
very bad. My picture is bad. I should have shown that. Yeah, actually, since the the initial grid was not very much squared, and that's why the problem occurred. Uh, so if you take these coordinates and draw a fair picture, you will see that uh, these parallel lines is along T1 actually. But the way I drawn it, I made mistake because the initial grid was not properly equispaced. I mean, they were not square. That's why the problem occurred in the drawing.
sir,
Sir, you have
actually, you
marked
use the Vivo.
minus 2 comma 2, I think, sir, in that V vector. And you have
Yes, sir.
written
The V
minus 1,
vector would
2.
have.
So, sorry, once again.
You've taken the vector as minus 1, 2, right? But you have marked on the diagram as minus 2 comma 2. So that's why the diagonal line is off.
Oh, right, 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 right. Yes, yes, yes. Thank you. I made this mistake. Yes, yes.
Yes, sir.
If you do that, it will come correctly.
Right, right, right. So minus 1 comma 2. So it should, the vector should be here, right?
Yes, sir. And the
So this
dotted
should
lines
be
would be
V.
along.
V is minus 1 comma 2. And now the dotted line should be along that.
Yes, sir.
Yeah, thank you for pointing this out. Now we can have the dotted line like this. Right?
Yes, sir.
Yeah. So these dotted lines are the new, uh, I should not say x-axis because the TE1 axis. It's all dotted lines are parallel to TE1 axis. Okay. Is it fine now? Any doubts about the picture?
No, sir.
No. Any further question, comments, doubts?
Sir, one comment I had that,
Yes, yes.
uh, sir, we know that R2 and R3 are equipotent sets, and so we can always have a bijection from R2 to R3. Uh, we can have a bijective function from R2 to R3,
Hmm.
but
And
I'm not sure that it will
how
be
to then
linear.
construct?
Yes,
Right,
no, no,
right, right,
we can construct
right, right.
also that
We can,
bijection.
right, we can construct. The question is that will it be linear or not? So
Yes,
you're
sir.
still thinking about this question. Yeah, right. So I also want you to think in that way. So uh, no, that was the same. Okay, okay. Find. So do you have any transformation in your mind? The bijection from R2 to R3, any specific form that you can verify?
Yes, sir. Means while doing set problems, I with your
No.
method of interlacing that decimals, interlacing those decimals means you give the idea of block.
Hmm,
Means
hmm,
you were doing
hmm,
the
hmm, hmm,
bijection from R to R square.
hmm,
So
hmm, hmm. But that will be linear. Actually, may not be a.
Uh, 0 comma 1 cross 0 comma 1 cross 0 comma 1.
Hmm, hmm, hmm.
So that bijection can be done, but sir, it is not linear. That
Hmm,
method
hmm.
of interlacing the decimals.
Right, right, right. That's not linear. Hmm.
And I cannot think of any linear bijection, linear transformation that can lead to the 2D plane to all the 3D space.
Hmm. Yeah, so there will be a problem in the linearity, of course.
Sir, actually, if we go from 3D to 2D, that kind of a linear map we can get. But
Right, right. That what you can do that x comma y comma z equals to x comma y. You omit the third coordinate.
but sir, that sort of a linear transform will have a determinant 0, so it cannot be invertible. Does
Right,
that mean that
right,
from 2
right.
to 3 we cannot have a linear map?
No, but you're talking about a specific map that is invertible. But that is not the proof that you cannot have a map.
Okay.
Okay.
Sir, I can think of small explanation that a linear transformation from R2 to R3 will be the linear combination of x and y, and means some equations giving a linear combination of x and y to x, y, and z in R3.
I could not get your point.
Means there will be some equations
Hmm,
which, when we put the value of x and y in those
hmm,
three equations, it will
hmm,
give you the value of x comma y comma z in R3. Means there are three equations, and I am put three equations in terms of x, y, in terms of x and y.
hmm,
Equation 1, equation 2, equation 3. In equation 1, if you put the value of x comma y, it will give you
hmm,
the new value of x coordinate in R3.
hmm,
If you put x comma y in equation 2, it will give
hmm,
you the value of y in R3. If you put x
hmm,
comma y in equation 3, it will give you the
hmm,
value of z in R3.
hmm. For example, in this case, I mean, you have x comma x plus
Yes,
y
sir.
comma y. Hmm,
Yes, sir. Now, sir, here there are three equations and, sir,
hmm,
two variables, x comma y.
hmm, hmm, hmm.
So, sir, this is an constant system of equations. Means
You're right. You're right. You're
so you
right.
cannot have
Yeah.
after
Solution.
fixing two
Hmm,
values, your
hmm,
third
hmm,
coordinate is automatically getting constant.
hmm, hmm. Of course, that's what we discussed. That the linear combination of the other two must be,
Yes, sir.
and
So
that's
you
why the
cannot generate.
solution
Yes, sir.
space cannot be the whole space.
Whole
It has a
whole
constant. Yeah.
R3. Yes, sir.
Right. 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 That's the constant we have.
In this particular linear transformation of this that you do, it just rotated, or means somewhat deformed the xy plane itself.
Yes. It actually shearing kind of
Sheared.
stuff.
Yes, yes, sir. Sheared is the word.
Sheared and the rotation also.
Yes, sir.
Yeah, we discussed those shear and rotation and reflection in the next class. So today we have a constant. So do you have any other question, doubts about the linear transformation, whatever we have covered until now? So what I said that to know that how, I mean, for any vector v, what will be the new coordinates of this vector? If you know that the new coordinates of E1 and the new coordinates of V2, that will give us a matrix that will be enough if we don't know the formula for the linear transformation. So that's why a linear transformation can be also represented by a matrix. It's not the complete sentence. There is a role of a basis that we'll discuss in the next class. Okay, so if you don't have a doubt, then I stop here. Thank you. And so we see each other tomorrow.
Thank you, sir.
Thank you, sir.